So let us start. Okay. So suppose let us again take Rn, and suppose F and G are two linear maps from Rn to R. Right. Then I can look at set of x in Rn, this F, so that f of x is 0, also g of x. So there are two constraints now, right? It's like in R3, I set y equal to 0, z equal to 0. These are the two functions. Okay. Then what you get will be the straight line, the x-axis. You understand? So what is the dimension? 1. Therefore, you expect the dimension may drop by 2. But be careful. Do you think it will always drop by 2? No. Why? Because suppose my f of x equal to a1x1 plus a(n)xn, and g of x equal to b1x1 plus bn(xn). Okay. Now, therefore what I am asking is summation axi0, summation baxi0. Can I expect the dimension will drop by 2? No. If f and g are scalar multiples of each other, that is linearly dependent, that is the vector a1 an and the vector b1 bn, okay, we are assuming these are non-zero. Okay, they are linearly dependent or scalar multiples of each other, then dimension will only drop by 1. Therefore, what is the condition I need? Okay, to claim dimension of w equal to something like n minus 2, I require f and g to be linearly independent. That is the vectors a1 an and the vectors non-zero vectors b1 bn are linearly independent. You understand this? And similarly for k, suppose I have something like k constraints f1 f2 fk, they are all linear maps from Rn to R, right? Then I can ask w to be x in Rn, so that fi of x is 0, 1 less than or equal to I less than or equal to k. Then I want to know its dimension is n minus k. So what should be the condition I should impose? I'm sure all of you guessed it, right? That is the set of f1, f2, fn as linear maps from Rn to R, they must be linearly independent. Okay, this follows by induction. It's very easy. Okay, just to pause, review, and proceed. Now, okay, now all of you are good. Now you should know what is the next question. Okay, now suppose I have a open set u in Rn open, and suppose I have two constraints f and g from u to R. These are C1 functions, continuously differential functions. Okay, then I want to know, let's look at, let's assume for with a loss of generality, okay, the a in u is that f of a equal to 0 is also equal to g of a. It need not be, f of a may be some b1 and g of a may be my some b2. Okay, so what I am looking at, I am looking at this x in u, so that f of x equal to 0, or if you want to call it b1, and g of a equal to b2, f of x equal to b1 and g of x equal to b2. But for convenience, we will always assume b1, b2 are 0, so that I can write as a, okay. Then I want to know whether locally dimension of s, we had already defined dimension of s. Do you remember that? Whether it's equal to n minus 2. Okay, when can I say that? If I understood my yesterday's lecture and today's the beginning, I'm sure that you know what the answer should be. Even for it to drop by one dimension, what was the requirement we needed? Around a, that is locally around a. Okay, what are the condition we needed? Delta fa should be non-zero. And similarly, if I want the dimension to be dropped by the condition g of x equal to b2, okay, then I want the condition a to be non-zero, right? So do you think if I impose these two conditions, dimension of s will drop down by 2? No. What should I require? Just because of earlier thing, what I require is delta FA and delta GA should be linearly independent. Right? So now RP. Just make sure, try to convince. As I said, 30-40% of understanding. This gives you intuition, the geometry, and even analytical prowess. Okay, please understand. Right? Therefore, suppose I have F1 to Fk from U to R. Okay, these are all C1 maps. And let's assume that Fi at A equal to Bi. By I is all I am assuming, right? Then I am looking at the surfaces set of all x in U so that Fi of x equal to 0. So this is not empty. Okay. So what is that I want? I want to say locally around A, dimension of S should be something like n minus k. So what should be the condition? All of you know that, right? So the obvious condition will be delta Fi at A. This set should be linearly dependent. Linearly independent, sorry. You understand? Yeah? Yeah. These gradient vectors, these k vectors should be linearly independent. Right? Okay. Have you understood? Now we are ready to format it in a slightly different language. Suppose this F1, F2, Fk, the constraints as given, therefore I can think of a function from U to Rk now. Okay, what is that? F of x to be F1 of x, Fk of x. Okay, these are all seen. You understand that? Okay, right. Therefore, now I can ask a very simpler question. This set S is nothing other than set x in U so that capital F of x equal to 0. Therefore, A belongs to this. I am assuming, of course, Fi of A is 0 for all I know. Do you follow that? Are you convinced? These are the same, right? Therefore, what should be the condition on F? Okay, this is same as saying F1 of x is 0, Fk of x is 0. Therefore, I know the condition should be the gradients should be linearly independent. Now, can you think of it? If you remember, please go through my lectures on several variable calculus where I talked about derivative, Jacobian, chain rule, etc. Okay, these things are not very well taught and neither they are understood properly. I'm sorry if I sound very negative, but that's the truth. Please go ahead. Okay. So if you remember, my del of x is not the first column vector is the gradient of f1 at x, and the kth column vector is gradient of f at x. That is, this is Jacobian. Okay, Jacobian matrix of this. Therefore, it is del f1 by del x1 at the point, okay, at whatever point, let us say if you want at A, and del f1 by del xn at A, and so on. Del f1 by del fk by del x1 at A, del fk by del x n at A. Okay. Now saying these column vectors are linearly independent is same as saying this matrix has rank k. Do you understand this? Therefore, the Jacobian matrix, notice that D of A is a linear map from R to Rk, right? And this is a linear map. What is the maximum possible rank? D of A, it is k. So what you are assuming is, okay, instead of saying this del Fi at A are linear independent, I can as well say, look at this capital F, which is a map from U to Rk, then the derivative of F at A should have rank k. Have you understood? Then I expect, okay, there exists, this is my S, this is my U, and this is my A. There is an open set U, UA, right? And this portion, okay, UA intersection S. That's what I mean by locally is, okay, as dimension n minus k. And not only that, this portion is also a graph of a function. Okay, please pay attention. Okay, pause, review, and then proceed. If you had understood, I am ready to formulate the implicit function theorem. Now you will see it's so crystal clear how to understand. But before that, again, I have to make sure that you understand the basic concepts about differential calculus. Okay, if you have gone through my lectures, you will have no problem. Earlier lectures. So we are going to change the notation. So let us look at, suppose I have Rn plus Rk to some Rm. Maybe I can write Rm to Rk. Okay, suppose this is a function here. Forget all the thing. I am essentially trying to review basic concept about derivatives and partial derivatives in a form which we need. Okay, again, you may not have seen this carefully. It's a very unfortunate. But if you have gone through my lectures, sure, you will do. Suppose A, B is a point. This may be an open set U also. Okay, right? Assume this is differentiable. Okay, what does that mean? Derivative of f at AB will be a linear map from R n plus m to Rk. Right? But notice that we want to understand it better. So I can talk about, okay, fix B, then I have a map, namely x going to f of xb. That is a map from where to where? Okay, okay. Just if you want, think of Rn so that it will be easier, Rn to Rk. Right? The derivative of this map is called the first partial derivative d1f at a. Okay, derivative of this of f at the point AB. Okay, that is called the first partial derivative d of f at a. And similarly, you can define y going to f of a comma y. Okay, that will be a map from Rk to Rm to Rk. Okay, the derivative of f at AB of this map, this it's not f but this restricted map. Okay, of restricted map f, that is called second partial derivative of f at AB. Do you understand this? Yeah, if you want to call it, you can call fb at x equal to this, and this is fa at y equal to this. Therefore, derivative of fa and this is derivative of fb. Okay. Now, what does one know? If f is differentiable at AB, okay, then if you give me a vector in a hk in Rm cross Rn, because any vector will be, I can split it into the first m coordinates, the second n coordinates. So let me call them as, this k will play a spoil, okay, this notation, right? Okay. So let us do that. Okay, let me call it h1 and h2 then. Yeah, okay, right. Therefore, my d of a b acting on this vector h1 h2 must be a vector in Rk. But what is this vector? Now let's look at the partial derivative. First partial derivative is going to be a linear map from Rn to Rk, and my h is in Rn cross Rm, right? I'm sorry again. Okay, where is my h1? h1 is in Rn and h2 is in Rm. Yeah, therefore this will be derivative of f1 at AB acting on h1. Do you understand this? Because f1 is a map from where to where? Rn to Rk. Therefore, the derivative of that map, namely f at fb at the point a comma b at the point a, if you want, that is what we denote by derivative. This will be a linear map from Rn to Rk. Therefore, I will get a vector in Rk. And similarly, the other one, it will be d2 of f of ab at h2. Okay. Please understand. In case you have not seen, this is very easy. Okay. But don't worry about the proof. If its proof is actually easy, but don't worry about the proof now. If this is the first time you are seeing this kind of partial derivative, please pay attention and understand. Okay, and if you have gone through my videos, these things will be much easier for you, of course. Right? Okay, now we are ready to formulate the theorem, the so-called implicit function theorem. Okay, so what does it say? So let U be an open set in Rn cross Rk. Don't worry about M and N now. I'm just using a different notation. All right. Let okay F be a function from U to Rk. Let the point AB, call it P, be in U. Therefore, A is in Rn, and I think of B as in Rk, a vector in Rk. You understand that? You follow that? Yeah, right. See there. Then what we want is, let's further assume f of AB is some constant, but let me assume as usual 0. Assume this. These are all part of assumption. I am assuming this one is C1 map, C1 function. Right? This is what I called capital F earlier. Yeah. What I call capital F is what I'm going to call small f now. Okay? Do you follow that? Therefore, I can form the set S as I did earlier. Okay, the set of all x comma y in U. Therefore, x is in Rn, y is in Rk. So that f of x y is 0. Therefore, notice that the point A, P, namely P, belong to S. So, what are we looking at? We are looking at constraint, that is set of xy, so that f1 of xy is 0, f2 of xy is 0, fk of xy is 0. If I write as fs, f1 to fk. Do you understand that? Yeah. Now I want to say this is of dimension. Okay, the total dimension of U is n plus k. Do you understand? It is a city. It's an open set in n plus k space. Therefore, how many constraints are there? F is taking values in Rk. Therefore, f1, f2, fk. There are k constraints. So I want the dimension to drop by k. That is n plus k minus k. That is n. Therefore, I want to say this dimension is yes. So when can it happen? We already know that. What did we know? Look at the derivative of f. Okay, and it must be of rank k. Yeah, do you remember that? So assume that rank of df at AB is k. Right? Then I want to say dimension of S is n. Pay attention. Do you follow that? Okay. But to make our life easy, what you'll assume is, in fact, we assume that the second partial derivative of AB, notice that that will be what kind of a map? Okay, that is a map from Rk to Rk. Okay, so I want it to be non-singular. This is same as saying has rank k. Right, because k-dimensional space to k-dimensional space. Please pay attention. Okay, do not get confused the notion, the change of notation. That's why the concepts should be clear. If the concepts are clear, notation will not bother you. Okay, right. So what I am assuming is there are k constraints. So if I write down the Jacobian matrix, okay, let us write down the matrix. So how will it look like? It will look like something like this: df1 by dx1, df1 by dxn, and df1 by dy1, del y1, and so on, del fy1 by del yk. Do you understand this? And similarly this. So I have this k cross matrix. Okay, this matrix is a k cross k matrix. So generally it's a del f by del yg. I and j varying over k. You understand that this matrix is non-singular is what I am asking. Right? Do you follow that? If you remember your matrix rank definition, these k rows are linearly independent. Therefore, the matrix column rank must be the same. That means the column matrix is, the set of columns is linearly independent. Are you clear? Sure. Do you follow what I'm saying? This is that linear algebra must be very strong. Okay. These k rows are linearly independent. And since row rank equal to column rank, therefore columns, k columns are linearly independent. That means my delta fi at a, this is at a, all the derivatives at a. Okay, these are linearly independent. Okay, so this is again, I wanted to formulate the theorem, but I'm sorry, I have to explain that, so I did that. So we assume, so this portion you can ignore. This is for your understanding. Ignore this non-singular. Then what do I want to say? Then I want to say there exists, then there exists an open set U1 in Rn so that A belongs to U1, okay, and open set UA in Rn, UP in Rn so that P belongs to UP and that's contained in U, okay. There exists an open set U1 in Rn. I said that A belongs to U1 and there exists an open set UP in Rn so that P belongs to UP and a C1 function G from where? From U1 to where? To Rk. So that now let's look at UP intersected with S. Okay, I will draw picture in a minute. This is nothing other than graph of G1. That is set of all x, comma gx, x in U1. The picture is the same as I have been drawing many times. Okay, two-dimensional picture is already good enough. This is my S, this is my P, that is A comma B, and I want to say there exists an open set UA. Okay, now I have, this is my A here, okay, and this is an open set U1 here, and there is a function G, this is U in Rn, this is in Rk, so I have a function U from this to here. That is my G. Okay, and if I take the graph is going to be this. The graph is going to be this portion. Okay, this is all we have been seeing, okay, since last lecture. Please understand. Is the theorem clear? In particular, let me go back. So in particular, this is the usual version you will see in all textbooks. In particular, for every x in U1, f of x gx is 0. Why? Okay, this is UP intersection S, therefore for x in U1, this is UP intersection S, but the point has to be in S. Okay, what does that mean? Are you following? Yeah. So this is this point x comma gx, call it as something like x comma y, that is in S. Okay, if it is in S, that means f of x y must be 0. That's what we are saying. Okay, so this is the theorem. So statement is over with this. This just an explanation. So pause, review, proceed. Okay, let me see how much time I have. See, understanding the statement is more difficult and it's utmost important. Okay, because the proof is, in my opinion, is easy. Okay, but you see that about we looked at the dimension. You only see the textbook like this. For x in u1, which is in a neighborhood of a, f of x gx is 0. That's all they will write in all implicit function theorem. But we have understood much better. What did we understand? Locally, its dimension drops down from n plus k to it becomes n dimension and 1. And second, locally it is going to be a graph. In fact, that is why we concluded the dimension. You understand that? That's how we define dimension. Please recall. Okay, towards the end, that's what we did yesterday in the first lecture. Okay, the proof is easy, as I said. First I will explain the idea, then we will go back. Okay, proof. So how does the proof go? So the proof uses inverse function theorem. Okay, but you remember inverse function theorem, what does it talk about? It talks about a C1 map from Rn to Rn, that is with the same dimension between two vector space of the same dimension. Okay, Euclidean space of the same dimension, right? Now what we have now? We have a map F from Rn plus k to Rk. If I want to use, what should I do? I have to hike up the dimension of the codomain, because I cannot drop it down here because I want something to capture with little f. Okay, so I have to hike up the dimension. And second thing is, remember inverse function theorem, want the derivative of some point, okay, that should be non-singular. That means what should I have? So please understand, I am trying to motivate how to think. Therefore I have to hike up the thing as a map from Rn cross Rk, that is your u, to Rn cross Rk. Okay, so I have to think of a map, call it a capital F, in such a way that derivative of f at ab, because that's a point we are local, because inverse function theorem also says something about when the derivative is not singular at that point, locally something happens. Okay, here also it says locally, therefore the condition should involve the point a comma b, that is our p. This should be non-singular. Okay, right? But this f should be built out of little f, then only I can get some result about f, right? And what do I know? Go back to what I said about Jacobian. This is non-singular, right? So how do I make use of it? Okay, this k by this matrix is non-singular, so what do I want is something else. Okay, it's very easy, don't worry. F of x comma y goes to x into f of xy. Notice that x is in Rn and therefore this is also in Rn. And little f maps Rn plus k to Rk, therefore this is in Rk. So I have a map from Rn plus k, of course this is u, in Rn plus k to Rn plus k. Do you understand this? Sure. The first n coordinates are mapped to themselves, but the second k coordinates, what do? f1 of xy, f2 of xy, fk of xy, that is f of xy. Do you understand? Therefore, what is the Jacobian of this? Derivative of f at ab. This is going to be identity. This is n cross n. Yeah. And here it's going to be 0. And here what is it? This is going to be d1 of f ab. And this is d2 of fab. This is something like dfy by dxj, and this will be del fy by del yr, where 1 less than or equal to r less than or equal to, or maybe del fy 1 I and r less than or equal to k. Here I less than or equal to k and j less than or equal to n. Okay, you understand? Now therefore determinant of this is determinant of this into this. This is non-singular, therefore d of a b is not 0. That is d of AB is non-singular. Pause, proceed. This is a very important construction. Please learn that. This is the typical way you will be using inverse function theorem. Whenever the dimension do not match up, you think of a way of constructing a function out of the given function. From little f, you constructed a capital F so that we can apply inverse function theorem. Okay, this is a trick. Please master this well. Right. So what does the theorem say now? So let us look at the picture. So I'm going to now look at the picture. First explain the thing. This is my U in Rn. Let me look at Rn like this. This is my Rn. This is my Rk. So this is my X. X come from here, Y come from here. And this is my point AB. Okay. This is my point P, which is A comma B. Right? So what does the theorem say now? So I have a map from capital F from Rn plus K to Rn plus K, and it's non-singular at the point AB. Therefore, there exists an open set. Okay, call it U of P. So that F maps U of P onto an open set. Okay, for example, call B. Okay, in Rn plus K. Okay, this is bijective answer that F inverse is also C1. Okay, so both ways. So what you call C1 diffeomorphism. Again, if you have gone through my inverse function theorem, you know all these words. Okay, therefore F as well as F inverse or C1. This is open here. Right? Now, notice that what is F of AB? F of AB is A comma F of AB, which is A comma 0. Okay, therefore this point will be A. Okay, therefore this V will be an open set containing A comma 0. You understand that? Therefore V an open set containing A comma 0, which is F of A. Yeah. Now what I can do is, okay, I can assume that this open set containing this is product of two neighborhoods. Okay, this is my U1 and this is my U2, that is here. Okay, this is my U2 and this is my U1. Therefore, I can assume U1 V is of the form U1 cross U2. Do all of you understand what I mean? Suppose V is open set containing A0, then okay, using product topology, okay, it should contain a product neighborhood. Product neighborhood is product of neighborhoods of A and product of neighborhoods of 0. That I am calling U1 cross U2. Please pay attention. Okay, so you can see we need linear algebra, we need topology, we need differential calculus to understand this. Okay, and geometry also to appreciate this. Yeah, so I can as well assume this, right? Cut it down, and suppose U1 cross U2 is A comma 0 is here and it's contained in V. Therefore, what I can do, I can take, since F is a diffeomorphism, it's also homeomorphism. Therefore, F inverse of V1 cross V2 will be some open set containing P. That set will be contained in UP. Therefore, I can restrict my UP to be that. Okay. Therefore, what I am saying is, therefore, without loss of generality, in fact, I proved it. We can assume F maps, okay, a neighborhood UP of P in Rn onto an open set of the form U1 cross U2 containing A comma 0. Okay, this is a diffeomorphism. So here from UP to U1 cross U2 is a C1 diffeomorphism. Okay, this is all out of inverse function theorem. Okay, now we are ready to cook up G. That's it. Look at the geometry, you will see how easy it is. So let me give it a different name. So let me call this as, this is my u1. Okay, this is my u1. My a comma 0 is going to be there, right? Okay, so now I'm going to construct a map. How am I going to look at u1? This is in Rn, right? And from here I go to Rn plus Rk. What is the map? Take any x, map it to x comma 0. Do you understand this? So this is my u1. Okay, my a is here, so this goes into a comma 0 here, right? Now remember, my f is the C1 diffeomorphism from this UP onto U1 cross U2. In particular, F inverse okay, that will be a diffeomorphism of U1 cross U2 onto UP, right? Therefore, I follow this up. This is going to actually sit in where? UP. Okay, U1 cross, let me change the color, U1 cross U2, right? This it is going to sit in this neighborhood. Therefore, and from here I look at F inverse. Where does it land me? It lands me in UP. And where is it? It is in again Rn cross Rk. Yeah. So I start with an x here and I get a point here x comma 0. Then I look at F inverse of that. So it will land somewhere in UP. And I want to say where it will land. Okay. And then what I do? Okay, let's look at that. Where does it land? F inverse of x comma 0. Of course, it's in UP. I say it is also in S. Why? See, remember, F inverse of x0, suppose it's a point xy in UP. You understand? Because F is a bijection from UP to U1 cross U2. Therefore, if I take a point here, it has to be in UP. Therefore, there is no problem, right? But then, what does it mean? That is, f of xy must be equal to x comma 0. But what is f of xy? This is x comma f of xy, right? You follow that? Therefore, the point xy, where does it lie? It lies in S. Because it is set of points xy such that f of xy is 0. Please pay attention. Okay, this must be a point xy. I know it is in UP. I want to say xy is in S. If I want to say it's in S, what do I have to prove? I have to prove f of xy is also 0, right? Since you told me f inverse of x0 is xy, that means if I apply capital F on both sides, what should I get? I should get capital F of this will be x comma fxy. Capital F of this will be x comma 0. Therefore, this must be 0. And equating the second coordinates, I get f of xy equal to 0. Do you understand? Pause, review, proceed. Yeah? Right. Now, let's look at. So, I have this map. Is this map? It's actually C infinity, smooth map. Okay, in particular C1. Right? X gamma is a linear map. Restriction of a linear map, right? And this F inverse by inverse function theorem, since this is C1. Yeah, go back. What are the map? The capital F was xy going to x comma f of xy. The component function, this is a C infinity function, whereas this is a C1 function. Therefore, this capital F is a C1 function. Okay? I should have mentioned that before computing the derivative. I forgot. Okay. Right? So that's a C1 function. By inverse function theorem, F inverse is C1. Now this is going to land in Rk. Therefore, I can project on the second coordinate. So I get a point. So I have start with an x. It goes to x comma 0. Then it goes to some point. Okay. And project it onto this. Also notice that the x coordinates are the same. Did you follow that? If I take x comma 0 and f inverse of x comma 0 is some x dash y dash, but okay, Yeah, but why should it be x? Because I should have f of x dash y dash should be x dash f of x dash y dash, but that should be x comma 0. Therefore x dash must be equal to x, and f dash x dash, that is f of x dash y dash, must be 0. Are you following? Please pay attention. Okay, if you begin to think, there is a possibility you will get confused. If you simply memorize, it's easy. You follow? Let me repeat the proof. I know f inverse of x comma 0 is some point x dash y dash. Okay, maybe let me call it u comma p. Okay, u and b are in r, u up, that is in rn, contained in rn cross rk. Right now I want to say then u is equal to x and f of uv is 0. These are the two things I want to claim. Okay, let us make sure. Okay, therefore if I apply f to both sides, okay, apply f to both sides, then what do I get? I get x comma 0. Here I have to apply here. What will I get? U comma f of u. So these two vectors are the same. That means my x must be equal to u. So I got it. And then f of uv must be 0. Right? Therefore, if I start with any point here, x comma 0, it's a pre-image here, like is of the form x comma some y. Don't worry about, okay, instead of b, I call it y. Okay, x comma y. Okay, and x comma y lives in up, but I also want to say it lives in s. Why? That's what we checked. Have you understood? So I have a map now. So we are ready for the construction of G. G is the map x going to x comma 0, that is from u1 to u1 cross u2, and this going to under f inverse. Okay, that goes to some x comma y. Okay, you know that x, it has to be x only. That's all we did, right? This is in u3, and this is from here. Look at the second coordinate, that goes to y. It goes to y, that is in rk. Yeah, therefore my G is the composite of these maps. Phi 2 composite f inverse composite, call it inclusion map. Inclusion map of Rn to Rn cross Rk, namely x going to x comma 0. This is a linear map. Okay, this is smooth, this is smooth, this is C1, therefore the composite is C1. Have you understood? Right, now we are through. We had already proved everything. So this is C1. Okay, very good. Next I claim for every x in u1, okay, f of x comma g of x is 0. Okay, that's what we just now did. Okay, where does, what is g of x? I of x0, that is x0, and f inverse, that is x comma y, right? And this x comma y lies in f, and this is what we call y is my g of x, and we know this is in s, therefore f of x comma y is 0. Okay, so this completes the proof. Okay, please, the proof is very simple, but then the ideas are deeper. Okay, so please review these two videos at least twice. First try to understand this feeling, what it talks about, and then get the proof. The proof, as you can see, is extremely simple. Yeah, so I hope all of you enjoy. Okay, please share your comments below. Thank you very much. Take care, stay safe. We will meet again. Perhaps as we will try to do something more about implicit function theorem, how to compute the derivative of g, okay, and then how to apply it to Lagrange multiplier in the next video. Okay, bye till then.